In this lesson, we are going to look at the proof of the quotient rule. As we have already learned in our previous lessons, we know that if f and g are both differentiable functions and then they are dividing, then the derivative of these two differentiable functions dividing is giving us this, and we are going to look at the proof of it. So we are going to prove it using the first principle, and we know that the first principle is giving us this. So what we are going to do here is to identify our f at x and then identify our f at x plus h. So from here we can say that our f at x, so we have f at x, that is the capital F at x, is giving us, so we are going to get f at x all over g at x, and then our f at x plus h, so we are going to have our capital F at x plus h, we are going to get small f at x plus h all over g at x plus h. So we are just going to substitute this into the first principle formula. So we are going to get the limit as h approaches 0 of f at x plus h is giving us f at x plus h all over g at x plus h, and then minus our f at x is what? F at x all over g at x, and the whole of this is over h. Now the next thing we are going to do here is to simplify the numerator. Okay, we have a fraction and a fraction here. We can use the LCM approach to simplify it, and we know that the LCM is going to be g at x plus h and then g at x, and then this will come and multiply this will multiply that. Very simple. Now with this h, we can write it, or we can bring it out to make everything easier and then simple. So you can write it in the form of this, and then we have a bigger bracket, okay, to make it very simple for us. So we know that in finding the LCM, this will come and multiply that, so we are going to get f at x plus h, then dot g at x, then we have our minus, this will come and multiply that, so we are going to get f at x times what? G at x plus h all over the LCM. Now what we are going to do here is to create and then destroy by adding 0 to the numerator. Okay, and we can add 0 to the numerator when we have negative f of x multiplying g at x plus f at x dot g at x. We know that this minus and minus, when they add together, we are going to get 0. So when we substitute this into the numerator, we've done nothing to the function. So we are just going to insert this into the numerator, and then let's see what we are going to have. So we have the limit as h approaches 0 of 1 over h. We have f at x plus h, g at x. Then we are going to insert this one into the function. So we have minus, let me use the black ink, f at x dot g at x, and then plus f at x dot g at x. Then we add our our last function, which is what? Minus f at x, and then multiplying g at x plus h. And we know that this is all over g at x plus h dot g at x. Now since h and g at x plus h dot g at x are denominators and they are multiplying, we can interchange their position. We can swap g at x plus h with g at x and then h. So the h will come here and then g at x will come here. It doesn't change anything since they are all denominators and they are multiplying. So we can do that. So let's do it. So we have the limit as h approaches 0. So we are interchanging their position. We have 1 out of g at x plus h dot g at x. Then we have our bigger bracket f at x plus h dot g at x minus f at x dot g at x plus f at x dot g at x minus f at x dot g at x plus h. And all this is over h because we have swapped their positions with. What we are going to do here is we are going to split this function, this side of the function, into two. So we are going to start the breaking from here, from this very part to this very part, and then from this very part to this very part. So this is how we are going to break it into two. So let's see how it is going to look like. So we are going to get the limit as h approaches 0 of 1 out of g at x plus h dot g at x. Then we are going to have bigger bracket f at x plus h multiplying g at x minus f at x dot g at x. Now we are breaking it into two. So we can write this as over h over h. So we have the over h here, and then we have this very part to f at x dot g at x minus f at x dot g at x plus h. And this side too is over h. Don't be worried about the h and h. When you have two fractions multiplying, they have the same denominator, we can pick one. So when we pick one and then we add the numerator, so don't be confused about these very parts. So looking through this very function, you can see that we have g at x, g at x. We have f at x, f at x. So why don't we factorize them out? So here we can factorize g at x out, and then this very part we can factorize f at x out. So let's do that. So we are going to get the limit as h approaches 0 of 1 out of g at x plus h dot g at x multiplying, we are factorizing g at x out. So we have g at x out, then we have another bracket within f at x plus h minus what? F at x. Then this, let's give the h to this very part. It doesn't change anything. And then this very portion too, let's factorize. F at x is here, f at x is here. So let's factorize it out. So in factorizing, we are going to get, we have f at x out. We are left with what? Now we can factorize the negative 2 out. So if you factor the negative out, this will change to what? Minus. So if this changes to minus, we are going to get g at x plus h minus what? G at x. And then let's give the h to this very part. Now you see, when we factor the h out, after expanding, we are going to get minus f at s g at x, and that is this very part. And then when we multiply negative and negative, we are going to get what? Positive f at x and then g at x. So we've done nothing to the function. The last but not the least step we are going to take here is to take the limit of each of the following functions here. So we are going to apply the limit on this, the limit on this, the limit on this, this, and then that. And then we are good to go. So in taking the limits on each of the following functions, we are going to get the limit as h approaches 0 of g at x plus h dot g at x. Then we have our macho bracket. So we take the limit as h approaches 0 of g at x, and then after that we come and take the limit of this very part too. So we have the limit as h approaches 0 of f at x plus h minus f at x all over h. They move to this very part. We take the limit also, the limit as h approaches 0 of f at x. Then we come to the last part, we take the limit as h approaches 0 of f at x plus h minus g at x, g at x plus h, g at x, and then we give the h to this very part. We are done. So we are just going to apply the properties of a limit, and then we see what we are going to get. So you know that when we take the limit here, the limit of this as h approaches 0, this h will go to 0, so we'll be left with what? 1 over g at x multiplying g at x, and we are going to get g at x all squared. Do you see that? Okay, good. Now when we take the limit as h approaches 0 of g at x, now since h is approaching 0, any functions of x can be treated as a constant, and we know that the limit of a constant is what? The constant. So we can say that this very part is g at x. Now this very part too, we can see that the limit of this function as h is approaching 0 is the first derivative from the first principle of the function f. So we can write it in the form of f prime at s. Good. Now we have our minus here. Now you can also see that the limit as h approaches 0 of the function f at x, and as h, the argument h, is approaching 0, any function of x becomes a constant, and the limit of a constant is the constant. So we are going to get what? F at x, and then this very part is similar to this very part, so we can write it as what? The derivative of the function g at x. So we have derivative of the function g at x. Now we have 1 out of g at x all square. Now let's expand and then see what we are going to get. So it means 1 will multiply the whole of this one here all over g at x squared. So let's rewrite it. We are going to get 1 times the whole of this, we are going to get g at x multiplying f at x minus f at x multiplying g prime at x, and all this over j x. And this is the proof of the quotient rule, which says that if two functions are dividing, if two functions are dividing, then the derivative is given as this. Thanks for watching.